So I hope you can see my screen, right?
Yes, sir.
Okay. So so in this class today, in previous classes we talked about one of the most important concept, that is hardware-software interface, and introduced the concept of instruction set architecture. So please recall what instruction set architecture is. So when you design a processor, that means a collection of, essentially this is a collection of some logical components, and it supports certain set of machine level instructions or assembly level instructions. So given a processor, if we look into the processor from the perspective of the set of instructions or set of machine language instructions supported by it, so then this collective attribute is called instruction set architecture. In computer design, in most of the cases, we first think about the instruction set architecture, and then go forward designing the appropriate hardware for it. At the same time, go above, to design software built on that. So today we are going to discuss some more features of instruction set architecture, and we will also talk about some fundamental model of computations. So our agenda for the next two classes is something like this. So we would introduce the model of computation and what is known as the Turing machine, and then we would talk about one of the most important concept in computer architecture, that revolves around what is known as von Neumann architecture, basic features of instruction set architecture, and then we'll introduce CPU performance equation and Amdahl's law, and touch upon risk versus ease, and if time permits, we'll talk about die yield and so on. Well, so imagine yourself that you are a computer designer and you are entrusted with the task of designing a processor. So you need to answer three questions. The first question that would arise, that you need to design the hardware, right? So how to design compact, efficient, and reliable hardware? That means how to design efficient logic, compact logic. It has to be compact because nowadays we are talking about millions and billions of transistors. So it has to be very compact so that it takes a very small area on silicon chip. It has to be reliable so that you can guarantee its functionality even after manufacturing and also during operation in field. And it must be efficient. Now, what do you mean by efficiency? So you always want that your chip or your processor would run fast. So that means the speed of the processor should be as large as possible. At the same time, in other words, the delay of information processing should be reduced. And at the same time, it has to be power efficient. Now, just think, imagine that you have a logic circuit. So in logic circuit, what are the possible values of the logic lines? Either 0 or 1, right? So that means from the physical perspective, it's a low voltage or a high voltage, maybe near 0 volt or near 5 volt. So when information is being processed by a logic circuit, what happens? So the hardware circuit has thousands of lines. I mean, the lines which interconnect the output of different gates to the input of some other gates and so on. So on these lines, the logic value would change from 0 to 1, 1 to 0, right? So imagine that you have a chip with billions of transistors, and the interconnecting lines or wires. Those wires are pulsating at gigahertz frequency. So what is going to happen then if there are so many transitions going on in a circuit, going from 0 to 1, 1 to 0, So what is going to happen then?
Lot of power consumption.
Lot of power consumption, yes, because as soon as you want to change the labels from 0 to 1 and 1 to 0, it means there are some inherent capacitances, right? Because these are physical devices, so there are inherent capacitances. Those capacitances will be charged and discharged, and in the process, it it would dissipate energy. So now just imagine this scenario that you have a small chip, you have a small processor whose area is very small, where so many transistors have been compacted, and each of them is pulsating with a high frequency, changing the status, changing the state between 0 and 1, 1 to 0, and so on. So therefore, they will dissipate an enormous amount of heat, and the chip might burn out. So therefore, you need this, has to be power efficient, it has to be energy efficient. At the same time, it has to be speed efficient. Okay, so there is a trade-off between this delay and power and this kind of thing. So when you design efficient hardware logic, you have to address this kind of issues. So this is the first challenge you have to solve. The second challenge is a fundamental question. So your purpose is to design a processor, right? So what does the processor supposed to perform? So ultimately, you are going to write some algorithms, and your computer is supposed to run those programs and give you output, right? So it has the power of it should have the power of processing some input information and to produce the desired output information. So here is the fundamental question, that in order to have computation, what is the simplest yet all-powerful machine model you need? Okay, so I want a structure of the machine. I want to visualize. I want to envisage the structure of a machine which is powerful enough so that it can compute, it can run algorithms or programs, but at the same time, it is simplest in nature. And this is the question which is answered this is the issue of known as the computability. And the third question is the following, that how should the basic computer architecture be conceived? Okay, so if you have a processor, you have an instruction set, and those instruction set can be executed by the hardware below. But imagine that, remember that each instruction requires certain hardware actions. That means a sequence of hardware operations. So how would that sequence of hardware operation be controlled? Right? So there are three challenges which a computer designer has to face. How to design an efficient logic or hardware? What is the simplest model of computer or yet all-powerful computing machine? And how should the basic architecture should be conceived? That means what should be an efficient mechanism for executing instruction one after another without an error? Well, so these three questions have been answered by three pioneers. So the issue of the logic design or logic synthesis has been addressed by Claude Shannon, and you have already studied this in your switching theory and automata courses. So in his master's thesis, a symbolic analysis of relay and switching circuits, Shannon introduced, he showed that the concepts of Boolean algebra, the Boolean algebra can be used for modeling the behavior of switching circuits, and the properties of Boolean algebra can be used to minimize or to optimize the cost of the logic. In fact, the modern logic synthesis, which allows you to design very large computers, also based on the Shannon's fundamental results. And the second question, that the issue of computability, was answered by Alan Turing, who introduced what is known as the theory of computability, that provides the basis for the fundamental requirement in computation. And the third question, concerning the structure or the architecture of the machine, was answered by John von Neumann. And you have heard about von Neumann architecture. We will discuss that. So he introduced the concept of, he introduced what is known as the blueprint of basic computer architecture. So you have, on one hand, you have methodologies for handling efficient logic design. If you study computability theory, that gives an understanding of what by computation, what do we actually mean. And von Neumann architecture gives you an understanding of basic understanding of the basic requirements of computer architecture. So we'll touch upon these issues one after another. Before that, this is an important look at this picture. You might recall that Alan Turing, who introduced this theory of computability, and he was an English mathematician and computer scientist. So apart from that, he was an excellent long-distance runner. Right? And not only he was a pioneer of theoretical computer science, he also introduced the basic concept of artificial intelligence long ago. Now, incidentally, Alan Turing has certain connection to India. His father served in the Indian civil service. Well, so what is computability? Let me touch upon it very quickly. So what is the simplest yet all-powerful computer? So we want to conceive a computing machine which should be able to execute an algorithm. So by algorithm, we mean some well-defined pen and paper methodology, which given some input would produce output and would terminate. Right? So what sort of hardware, what sort of basic hardware you need in order to execute any computation? So this is a fundamental question. So we want to conceive a computing machine or a processor which is as simple as possible. At the same time, it is all powerful. So what was that? What was that model called?
Turing machine.
So Alan Turing, he conceived a machine that introduces the model of computation. Look, this is a very fundamental concept. He conceived a very simple machine. All you need is a tape, which look like this. This is an infinite tape unending in both sides. And the tape is partitioned into cells. Each cell can store certain symbols. And those are called input symbols. There may be some blank symbols, some delimiters like that. So this tape is nothing but a memory. And in this tape, you can write or read. So we have a finite state control like just a finite state machine. So number of states in this machine, in this controller, is finite. The tape is infinite. The memory is assumed to be infinite, but the controller is assumed to have finitely many states. And the controller can perform the following action. It has a read-write head. So at an instant of time, it settles on a particular cell. So it can read whatever symbol is there. If necessary, it can move to the left, one cell right, and it can write some symbols from the alphabet, from the defined alphabet. So that's all. Nothing else you need. So the tape head can move left or right. And what are the actions you want to take? The machine currently is in some state, which is called the present state of the machine. So depending on the present state of the machine and the current symbol it is looking at, this controller takes certain action. So it moves to a new state. It may write a symbol here, or it may move one cell left, right, something like that. And the machine halts. The input, what you give, whatever program or an algorithm you want to write, that program has been encoded here, and the input is also encoded in the tape, and then you start the machine from the start state. The machine keeps on reading and writing and moving this head left or right, and finally, when this controller reaches an accept state, you know that in a finite state machine there are some accept states. So when the machine reaches an accept state, the machine halts, and the output can be read out from the tape. So this is the overall structure of a simple machine, and Turing showed that this machine is able to perform any sort of algorithm. Okay, so very simple mechanism. So what you have, You have memory, which is theoretically infinite. You need a control, a finite state control, some read-write capability, some shift, and some state, accept and reject, and so on. Okay. So this is the paper which Turing published in 1936. And there are many interesting stories here. You know, the Turing submitted this paper for publication in journals, and the reviewer said, your machines are too simple. As far as the current technology is concerned, there are more powerful machines available in the market, so your paper is rejected. Right. As you can see, even though it is a very simple mechanism, but it is extremely powerful. And there is a conjecture known as Church-Turing conjecture, which states that a function of natural numbers can be calculated by an effective method if and only if it is computable by a Turing machine. Now, in simple terms, it means that any procedure or algorithm that is computable by paper and pencil method can be solved by a Turing machine. So if you conceive of an algorithm which terminates, if you can write a set of instructions, a pen and pencil method, then that can be emulated, that can be executed by a Turing machine that can process your input and give you the desired output. So this gives you a lot of insight. So in order to design a processor, all you need is the following. You need some memory, you need a control unit, some read-write capability, some operations, and some indications of completion or accept reject kind of thing. All right. Now, since there are many limitations in every discipline, Turing machine has also certain limitations. Anybody knows that? Anything which is not any example of a problem or any problem which is not computable by Turing machine?
Halting problem.
Right, Turing undecidability. So there are some fundamental limitations in every discipline. For example, in special theory relativity, introduced by Einstein in 1905, what he did is the elimination of the notion of absolute time, based on the postulate that the velocity of light is constant. Gödel introduced the incompleteness theorem, which questioned about the notion of the absolute mathematical truth. And in a similar tune, Alan Turing introduced the halting problem of Turing machine. Is the algorithmic inability to identify the presence of an infinite loop in arbitrary programs. So what does it mean? What does Turing undecidability means? It is the halting problem. The question is, can you write a program Q which, given any arbitrary program P as input, would decide whether or not P terminates or falls into infinite loop on some input data? Now, observe that given a particular program P, whether or not it would terminate, that you can decide. But here the question of the generality for any arbitrary program. So given an arbitrary program P, which you have written, the question is whether it would terminate or would fall into an infinite loop on some data. And I want to automate this detection process. I want to write another program Q, which would take this program P as input and would decide whether or not P would enter in an infinite loop on some input data. The halting problem says that, well, you cannot do this you cannot write this kind of universal programming. This cannot be solved by a Turing machine, and hence this is Turing undecidable. So the presence of an infinite loop in an arbitrary program, that cannot be identified using another program. So it has a lot of theoretical consequences and so on. You would read more about this when you study the theory of computability and other courses. Just for the sake of what we talked about, Gödel's incompleteness theorem, it says that similar thing, that in any branch of mathematics, you have a set of axioms, right? You have a set of axioms and propositions or postulates. So based on that, in any branch of mathematics, there will be some statements which cannot be proved either true or false in that system. So that is what Gödel proved, and this is a very fundamental theorem in mathematics. It's called the incompleteness theorem. So these are similar to you, like halting problem of Turing machine, incompleteness theorem. They are similar kind of propositions. Well, now let us move into now the architectural space, which was, well, another thing is that today we are talking about this artificial intelligence and machine learning, but long ago Turing introduced this concept. So he thought that he asked this question: what you want is a machine that can learn from experience, right? So today we are thinking of we are conceiving machines which can learn by itself, right? Like reinforcement learning and so on. But long ago this was conceived by Turing himself. Well, in the architectural space, John von Neumann, a Hungarian-born American mathematician and computer scientist, he introduced what is called this von Neumann architecture. Okay, before that, let me present before you a very interesting question. On the left, you can see a diagram, and this is a simple model of a processor. All you know, we have already seen that in a Turing machine, you need a memory, you have some kind of controller and a sequence of operation, read, write, and so on. So imagine that you have a processor like this. You have a memory block here. And so this is the processor or CPU. It has arithmetic logic unit and controllers, data bus, and so. And it has two things. One is some registers are also here for which serves as local memory. And there is a special counter here which is called program counter. So we'll talk about the role of program counter in detail later. Now you know that when you execute a high-level language program, it is compiled to assembly language, and then assembler translates it into binary strings, right? So everything now becomes binary strings, a flat file of zeros and one binary strings, and those binary strings are stored in memory, right? So you input your program and data and store in memory to start with. So if we look into memory, now your high-level program is not there. All you have, everything what is in memory is just strings of zeros and one, right? Now imagine that you are looking into a particular content of this memory location, and assume that you have a memory word here which is 32 bits long, whose size is 32 bits. That means 4 bytes. All right. And the content of so imagine that you have a memory location X, and the content of memory location is this, which in binary is this. All right. So the machine at this point of time, suppose it is accessing this memory location and finds the content of this memory location is this. Is a binary string which comprises 32 bits, strings of zeros and one. So what action would be taken by the machine? How does machine know what is the significance of this bit string? Because when everything is translated into bits, all its inheritance is lost, right? I mean, whether it is an instruction or it is a data, if it is data, whether it is integer or floating point, what is it? How does the machine would take action, How does the machine correctly interpret the meaning of this string? You understand the question? Now suppose that you are confronted with this challenge. You are going to design a processor, and the processor, when it looks into the memory, it finds a bit string, a 32-bit bit string. Now, what the processor is supposed to do now? How would you solve this challenge? Because the binary string has no inheritance. It has lost all its meaning or connotations. Isn't so? Who am I is the question. What do you think?
So we can use some of the bits to encode that it is an integer or something like that.
Well, So if you have to do that, then for every string you have to do that, right?
Yes, sir. Yes.
Then it means additional cost. Bits are costly, right?
Yes.
And not only that, when the string becomes larger, it would take more time for transfer, more energy consumption, isn't so?
Yes, sir.
Whatever. So what are the possible alternatives? See, that's how the von Neumann architecture was conceived. So you are confronted with this kind of thing. Inheritance is lost. This is called the identity crisis, isn't so? Well, if this could be a 2's complement binary number, right? So had it been so, then X is something like this. If it is a 2's complement binary number, then the value of X would be this. But you are not sure. X could be a floating point number. It could be an unsigned binary number also. The machine, the processor is able to process unsigned numbers, signed numbers, all kinds of arithmetic operations are available. So if X is an unsigned binary number, then the most significant bit is not signed bit. It contributes to the magnitude. So then X would be something like this. It could be a floating point number also, a fractional number. Then the value of X is this, 1.8 times 2 to the power minus 96. This could be an instruction also. And in MIPS language, this bit string represents this instruction. Load word $T7. That means this is a register, and this is an offset value, minus 16,384, and this is another register. So how does you see this? There is an identity crisis. Now, how does the machine know how to interpret this string? And depending on the interpretation, appropriate action is to be taken, right? If it is an instruction, so then I need to decode the instruction and to see what kind of instruction it is and take the appropriate actions. If it is a 2's complement binary number, then it may be a part of some data, right? Or similarly, if it is an unsigned or floating point, it is a part of data. And I need to do some data operation with some other data and so on. Right? So the challenge is, how does the machine identify the attribute of this string? So in order to solve this problem, one of the simplest way you can do this is the following. You think of some cycles, some instruction cycles. You start with executing certain instructions, first of all, and so you start with some execution cycle. In other words, initially, whenever the processor accesses memory, the first binary string you encounter must be an instruction, because that should tell the machine what actions to be taken. So the first, it should be an instruction, and so you bring the string to the processor side. The processor decodes what kind of instruction it is. If it is an add, multiplier, or arithmetic operation, or logical, or shift, whatever, depending on that, the next instruction, the next action would be determined, and the identity crisis would be resolved based on the interpretation of the first instruction and so on. And this will continue. In other words, we need execution cycles to interpret binary strings properly, whether it is instruction or data. And if it is a data, then what type of data? So I think you have appreciated the challenge, and now we are trying to discuss the solution to it. All right. So von Neumann architecture, this is also known as Princeton architecture, introduced by John von Neumann. This is a stored program concept. So your program is a code segment, and that is compiled and assembled, and then you get a binary string, a sequence of binary strings. So your program is also a binary file. Your data is also a binary file. So everything is stored in memory. There is no distinction between program or data. So this serves as the basis of all modern computers. Instruction and data, just flat binary bits, just bits. No way to distinguish. If you look into memory, If you just look into memory, you would see these binary strings or these bits, and there is no way by looking into memory you would be able to discriminate between whether it is instruction or data or what type of data is. You cannot discriminate this. This is just inheritance. I mean, there is no inheritance. But how do we then interpret these bits? That you do in terms of a sequence of machine instructions, which is stored in memory, just as like data. So that you run those programs or instructions from memory and keep on executing one after another. And in the process, these binary bits which you access from memory would be interpreted one after another, would be interpreted correctly one after another. So you have a flat memory that stores data, programs, even compiler programs, systems program, OS, everything as binary strings, as bits. And in the instruction would come, there would be some fetch operation and execute operation and so on. We'll discuss that. And there would be a program counter, is a special counter here, which is called PC. And the PC points to the next instruction to be fetched from the memory. So initially the PC is loaded with some values of zeros and one, which gives you the address of the first instruction which is stored in memory. Right? Because fetching data as the first operation does not make any sense. The first binary bit, the binary string you have to fetch from memory must be an instruction, because this processor has to be told what actions are to be done, right? So the first binary string that you are going to access from memory must be an instruction. So PC is a program counter, is essentially a register. This register holds the address of the memory location where the next instruction is stored. So initially it stores the first instruction of your program segment. Any question here? Any doubt or you need clarification? Any question regarding program counter? It's a special register in the processor which points to the next instruction to be fetched.
So how does it know whether it's an instruction or just data?
That's why I told you, yes. How do I know whether it is an instruction or data? So suppose everything is in memory, your program and data, right? And your processor is on the left side. So what actions are to be performed? Something you have to bring from memory. Everything is in memory, your program and data, right? Now you need to know that from which location your program has been loaded in memory. Because in the operating system, you have these loaders and linkers and so on. So the system knows which is the first starting address of the program instruction. You understand? Are you with me?
Yes, sir.
Okay, so the program counter would hold the address of the first instruction to be executed. And then I will show you that once the first instruction is executed, then what next? How do we bring data and everything? But when the program is loaded in memory, the system must know the starting point of the starting address of the first instruction loaded in memory. Otherwise, the machine cannot start operation. And that address should be loaded into the program counter by the operating system. All right. So program counter points to the next instruction to be fetched. Now you tell me, suppose you fetch the first instruction, machine executes it, and in the process of execution, some data may be fetched from memory again, and that information that from where that data has to be fetched must be embedded in the first instruction. So we discuss this subtleties later. But suppose you tell me one thing, what do you think about this? Suppose you fetch the first instruction, all right, and the execution of the first instruction is over. What next?
So the first instruction, it should contains some instruction or some location of the second instruction.
No, but then the location, every instruction, if the memory address is long, because the size of the memory is substantial. So in order to access, in order to define an address of a memory location, so for example, MIPS. In MIPS assembly language, the address of memory location is also 32 bits. So if the first instruction contains the address of the next location, then the instruction itself would be, every instruction itself would be very long.
Yes.
Not only it has to contain the information about the instruction, but also about the address of the next instruction, right? So much information cannot be packed in one instruction, that would be too long.
Sir, so the instructions can be like stored consecutively in memory, like the program counter.
Yes, in consecutive in memory, yes, possible.
Yeah, so the program counter just has to update to the next address, which can be done using a small constant addition to the program counter.
Very good. And if we assume that all instructions are of the same length, okay, assume that all instructions are of same length, 32 bits, 4 bytes in my machine, then what will happen? Every time you increment the program counter by all instructions are 4 byte long. So,
32.
Right. So once the first instruction is over, you increment the program counter by 4 bytes again. So that would point to the next instruction. Clear? So by virtue of, however, if the instruction length is different, suppose in many machines, for example, in Intel processors, instructions length may vary, Some instruction may be 32 bits, some instruction may be 48 bits, then you are in a problem, Right? And that's why in MIPS or reduced architecture machine, all instructions are assumed to be of same length, 4 bytes in MIPS. And that simplifies the operation of the execution of the next instruction. Because I know that the program counter, once this instruction is finished, I know that the next instruction stays in the consecutive location in memory, which is 4 bytes apart from the first one in memory. So therefore, PC must be incremented by 4 bytes, and it would point to the next instruction. And the sequence is repeated. Are you with me?
Yes, sir.
Yes.
Okay. But what could be, suppose the first instruction is a branch instruction, then what will happen? And if the branch is taken, if then else, for example.
So jump to location, the new location has to be loaded into the PC.
Right. So that where to be loaded, that information, the target address must be present in the current instruction which you are executing, right? So that the program counter needs to be updated accordingly. So we'll talk about that. So you have understood the basic concepts, how the execution should be continued one after another. And now we would realize that how would I distinguish between instruction and data, and if data, what type of data? So if it is an instruction, then in the instruction there would be certain specific bits reserved for it. These are called opcode or operational codes. And these codes will tell you what sort of instruction it is, whether it is an add instruction or a logical AND operation, or it is a shift instruction, or it is a branch or if then else, what this kind of thing. Okay, so depending on your instruction space, you encode each instruction by a distinct opcode, and that opcode would occupy certain specific bit in your instruction, which may be assumed to be of 32 bits. All right. So you fetch the next instruction by this mechanism and continue. And this process is called the execution cycle, alternatively also known as instruction cycle. Now let us see how the program would execute and how to distinguish between program and data. So first of all, the first binary string which you are going to fetch from memory must be an instruction. So it should be so the program counter should point to the first instructions residing in memory. So the first step is the instruction fetch from memory. So what actions are to be taken here? The program counter is loaded with the address of the instruction. That address is floated into the program is the address bus. The memory receives that address, decodes that address, and locates the particular location corresponding to that address, retrieves the memory content, and passes it back to the processor side through data bus, through instruction register. All right. And once you know that whatever you have fetched from memory, it's now instruction. So the controller of your machine or the processor of your machine has been designed in such a way that in this execution cycle, in this phase of the execution cycle, it knows that I have brought an instruction from memory, right? So I need to interpret this instruction. So I need to enable the decoder circuit, which is built in hardware. So that would extract the corresponding bits from the instruction, the opcode field, maybe the first six bits or 8 bits or whatever, depending on the architecture of the instruction cycle, instruction set, format of the instruction set, and we decode those bits, and we know that, and then you determine what kind of instruction it is. Right now, if it is if this is an instruction, for example, add, I may need some kind of operand. I may need some kind of data. I know that some data has to be loaded or from memory or from memory again. So next time I will also initiate some access mechanism, and this time whatever bit string you are retrieving from memory would be some kind of data. So everything is under control, and once the instruction is decoded, that determines what subsequent actions are to be taken, whether there are data fetch operations and so on. So here one thing I want to mention, that in particular in MIPS architecture, which will be studied in detail in this course, so this arithmetic operation and data transfer operation, they are treated separately. In other words, if we have to fetch some data, there will be separate instructions for that. And if you want to perform arithmetic operation, there are separate instructions for that. And when you perform arithmetic operations, for example, add, it would be assumed that those data is already available in the registers in the processor. And in order to fetch those data, previously you need to execute certain load instructions so that those registers are loaded with the desired data from memory. So we talk about that later on. Let's not bother about so many complications, So you have instruction fetch, instruction decode, and then operand fetch. That means another memory operation may be needed. And then you execute it depending on what type of instruction it is. And you need to store the result. This is called write back. You deposit the result in either register or memory, and iterate this processing and fetch the next instruction and so on. How do I fetch the next instruction? By incrementing the program counter, if it is the next consecutive instruction, or by loading the target address if it is a branch instruction. Determine successor instruction. And that's how the execution continues. And in the process of execution, see, this identity crisis is automatically resolved. So when the system is in the instruction fetch cycle, so there are several cycles, as you can see, or small stages. So when you are in the instruction fetch cycle, you know that whatever you are fetching from, whatever bit string you are fetching from memory is an instruction. Now in the operand phase, there is this memory access, that means at the third stage here, if you are in this cycle, this portion of the stage, if you are in this stage, then you know that whatever bit string you are accessing from memory has to be some data. And whether it is a integer data or floating point data, that can be interpreted based on what type of instruction it is, which has already been decoded. Right? Because the floating point instructions and integer instruction, those are different in assembly language. So you already know that whatever operand you are going to fetch in the memory stage, whether it is an integer data or floating point data or it is a character data, whatever. In other words, so there are several stages in the total execution cycle, right? I think you got some overall idea. Any doubt here? Okay, so let me summarize here. So what are the features of von Neumann architecture that you have discussed? Same physical memory to save instruction and data. And if you look into them as flat strings, there is no way to distinguish between them. Okay. And since you have the same memory, and at one instant of time, the memory can be accessed only once because of the transfer mechanism and the transfer devices. So therefore, the instruction fetch and the data transfer cannot be done simultaneously. You need separate cycles. Just like in the previous case, see, the instruction is being fetched in this cycle and operand fetch is being done in different cycle. Now, what do you mean by cycles, by the way? How do we synchronize everything, Please tell me that how do you synchronize this? Because every stage needs some time, right? How do I synchronize everything?
So every stage can be given the same amount of time based on which takes the maximum time. The maximum time can be given to each stage.
Right, that you can do, but there may be variable times also. And how do I keep track of that time?
Maintaining a clock.
Maintaining a clock. So what happens, this instruction fetch may take several clock cycles because the clock may be very fast. Maybe the instruction fetch takes 5 clock cycles. Maybe the instruction decode takes 2 clock cycles. This kind of thing. So there is a synchronizing clock which keeps track of all kinds of, because in every stage there are registers or memory elements. When you fetch the instruction from memory, you bring it to the processor side, but you need to hold that value, right? So there are some registers which are called instruction registers, which saves the current instruction, because you have to save the current instruction until the operation of the instruction is finished, right? So in order to maintain those, you need several clock cycles which synchronizes all transfer operation. So there is an underlying clock which ticks all the time, and the instruction and everything is synchronized with the clock. Maybe the instruction fetch takes certain number of cycles, decode takes certain number of cycles, and so on. So in order to finish this, you need certain number of cycles. Those are called machine cycles, right? Clock cycles are also known as machine cycles. So each stage of this execution cycle may comprise several machine cycles. These machine cycles are needed in order to synchronize everything. Otherwise, there will be total mess, total chaos. Isn't so? So instruction fetch and data transfer cannot be done concurrently because you have the same memory in von Neumann architecture. And it's very simple architecture, as you can see. There is a variation which is known as the Harvard architecture, where separate instruction and data memory are kept. But more or less, conceptually is more or less the same, but this may be done. I mean, here, because you have 2 separate copies of memory, then the instruction fetch and data fetch can be done simultaneously, maybe expedited. So that we'll discuss later. So let us look into the full picture again. So we have 5 easy pieces. We have already seen that you have a processor here, and that means you have the arithmetic logic unit, you have a controller, and this is a very complicated finite state machine which would take care of what's the entire sequencing. And you have a memory here for storing both instructions, set of instructions and data. Processor in this side, you do not save anything, but there are some registers also available here which can serve as a temporary storage, because accessing memory is time consuming, right? And also you need this input output devices. So this is the full picture, and also for output you have this monitor or printer, for input you have keyboard, mouse, and so on. All right, let us look into this this mechanism, that how machine language programs are executed. Everything is in memory, right? So you have a binary string, you have binary bits or binary file, which comprises, you do not, this is a flat binary file, comprises instruction and data. So that you need to input to the machine using some mechanism. And then this is loaded into the memory. And when you load into the memory, you need to remember something, that you need to know that from which location you have stored the program, from which location you have the data file. And you also need to know the address of the first instruction loaded in memory. That information has to be passed to the processor to start with. So the program counter should know the starting address of the address of the first instruction loaded in memory. All right. So the program counter. So now the processor, whilst executing this program, first it looks into the program counter, sends this address to memory. So it points to a memory location, retrieves this content. So initially it knows that this is the first time you are accessing the memory. So this should be an instruction. So the content of the memory location is returned to the processor. You save it into the processor, and then the controller examines this bit string. Now, since it is an instruction to start with, the controller knows that, well, maybe the first 6 bits should represent the opcode. So depending on what strings you have here, the controller would take appropriate action. Whether you need to fetch further data and so on. So that would be determined by the opcode of the current instruction. Okay, so the controller examines this instruction and takes appropriate action. So the instruction says that, well, the content of register 4 must be added to the content of register 2, and the result should be saved in register 2 again. So that is the meaning of this instruction. And in this bit string, this information of the register 4, the identity of register 4 and the register 2 is encoded here. As you can see, this is the bit string, which 00100. It means that its value is 4. So it means this indicates this is register number 4. And this all 0 means it is some kind of addition operation. All right. So this means this is register 4. This is register 2, and the result you should put in register 2. That is the meaning of this instruction. So the corresponding data path is enabled. This arithmetic logic unit is activated, proper actions are to be taken, and the result is saved in the register. So everything is being executed, is being done following that execution cycle. All right, and then the next instruction is to be fetched and so on. And this continues. On program completion, the results is stored in memory, and it is delivered to the output. All right. So now, one thing is, so I tried to give you an overall structure of this von Neumann architecture. Now it has certain bottleneck. One thing is that it architecture, the same memory is used for instruction and data. And notice that memory is inherently slower than logic because of the technology. And there is also some kind of trade-off issues like cost and so on. That's why memory is inherently slower. Particularly the DRAM, the dynamic RAM sort of memories are slower than the static RAMs. And therefore, the access time, the time spent in memory accesses can limit the performance. And this is known as the von Neumann bottleneck. So in computer architecture organization, we would study this problem in more detail, and we'll see later on that how this bottleneck, how this speed limitation can be overcome, can be speeded up by several techniques, like on-chip register uses, use of cache memory, and so on. Let me present before you a complete view of computer architecture. So on the left-hand side, you see that these are the basic components in the processor. So you have registers, you have several registers, For example, in MIPS architecture, there are 32 registers here, which are which are supplied by the which are already resident on the chip. You have data paths. That means the paths through which you can pass the data from one component to another part. You have arithmetic logic unit for performing arithmetic and logical operation. And this is the controller, the most important thing. This is the brain of the machine, right? Under the controller, all actions are synchronized. So this is the processor side. The register can also be thought of some memory, but registers are essentially flip-flops. That means cross-coupled NAND gates or NOR gates with some additional logic. So that's why register access is much faster, but it is costly, So therefore, the main memory which you usually refer to is, so this is a little slower, because the memory technology here is called the dynamic RAM. So these are not flip-flops. Here, some transistors are used here, and the bits 0 and 1 that is stored as a charge, whether the capacitance is charged or not, and therefore the access of DRAM is slower, whereas the access of registers is faster. But there are cost issues, This static RAM. So here the registers are costly. DRAM is much less expensive. So because of the cost issue, the main memory is treated as separately, which are essentially a slow device. And not only DRAM, there is also hierarchy here, because you have secondary memory like flash, hard disk, solid state drive, CD, and so on. Also very large memories backup, like redundant array of inexpensive disk, data center network, and so on. In the earlier days, people used magnetic tapes and so on. And also there we have cache RAM. We have the cache memory, which is a faster kind of memory, and this is also called SRAM or static RAM. And this memory structure is called memory hierarchy, which will be studied in detail later on. And the purpose of the cache, this hierarchy, is the following: that it improves this memory transaction time. Most of the time, if you want to access here, it would be slower. Similarly, accessing hard disk or solid state drive is slower. Obviously, these are slow devices, isn't so? But in this direction, if I want to access cache, this is much faster than accessing main memory. Accessing main memory is faster than secondary memory, and so on. So what the processor does, it first looks into the cache memory. If the requested item is available here, then the transfer is completed. You do it very fast. If not, then you search in the lower level of memory and so on. So for some instruction or data, you may pay penalty, but for most of them, you may not. Most of the instruction can be executed faster. So we'll study about this memory hierarchy later. But this is the overall structure, and to speed up further operation, there is what is called an on-chip cache in the processor size also. So register, just the thumb rule is the following: register, on-chip cache, cache memory, main memory. These are all memory. Register is the fastest form of memory. This is next in speed, and this is again next in speed, and so on. All right. The purpose of memory hierarchy is to expedite, is to reduce the transaction time across the CPU memory interface. Now we demonstrate in next few slides that what kind of transactions are needed across this CPU memory interface. Well, so memory hierarchy we just touch upon here very quickly, that we have registers and then this L1 cache, L2 cache, main memory, hard disk, and network. As you can see that the capacity increases in this direction. Okay, CPU includes register and some on-chip cache also. So registers and some on-chip cache is the part of the CPU, and the rest of the memory is lying outside the CPU, and that's a separate memory modules for that, or memory components for that. And as you can see, if we look into this way, the speed and cost would increase. That means these memories are at the top echelons. Those are faster, but obviously, for obvious reason, they are costly. And in this direction, the capacity increases, but the speed reduces at the same time the cost reduces. So as you can see, there are many trade-offs. How do you organize your memory and so on? Okay. All right. So now let us now focus on our main issue, that instruction set architecture. Well, so this is that is a set of machine level instructions in a particular CPU implementation. It's called the instruction set, and that lies at the hardware software interface. So what are the when designing the instruction set architecture, there are many issues or factors you need to consider. Before that, let us recall that what should be the goal of what are the goals of designing an instruction set. The software above, the software engineers must be able to use this instruction set efficiently so that they can build their programs above it, right? And at the same time, the set of the instructions should be such that whatever hardware is necessary in order to support those instructions should be simple. So different CPUs have different kinds of instruction set, and depending on the corresponding implementation would be different. So what are the particular features that an instruction set architecture should have? First of all, the instruction set architecture, the set of instruction must be complete, right? It should be able to represent any operations you need. And moreover, you should decide what is the instruction formatting. Each instruction would require certain number of bits, right? So the first question is, what is the length of my instruction? How many bits are required in the instruction? Whether it is fixed or variable, that is a fundamental question. Whether all my instruction would comprise the same number of bits or it may be variable. For example, in MIPS architecture, the instruction format is fixed. But in Intel machine, the instruction format may be variable. So that is one issue, one question here. Other thing is what is the format of my instruction? How many fields are there in the instruction? There should be opcodes, right? Some bits should be reserved for designating the instruction, to identify the instruction. How many bits do we need? And where should I place in the formatting? Some registers you want to specify in the instruction itself, right? So you need register IDs. Or the number of bits you need to identify the registers. How many operands or memory address you want to specify in an instruction. So depending on these issues, the length of the instruction would be determined, right? That would determine the length of the instructions. So when you are designing the instruction set architecture, you have to consider this kind of factors. Size of the logical address space. So that means, so we said that in order to access memory, I need to send the address of the memory location, right? The CPU must float the address of the memory location. So here a natural question is, how many bits in the address bus? How many bits should be given to access the address? If I have k bits, it means that I can access 2 to the power k memory locations, isn't so? For example, in MIPS architecture, the size of the address bus is 32. That means you can access 2 to the power 32 what? 2 to the power 32 bytes. Any question here? And this is known as the logical address space. How many instructions should be there? How many machine level instructions should be there in your machine? And depending on the number of instructions, that would determine the number of bits in the opcode, because the number of bits in the opcode must be the log of the number of instructions, ceiling of that, right? So if I have, for example, if I have 64 instructions, I should have 6 bits in opcode. What are the different instruction types that you need to decide while designing the instruction set architecture? There must be some arithmetic operations. It should include integer operation, floating point operation. There should be logical operation like performing bit by bit, ANDing, ORing, XOR, and so on. Data transfer data from memory to the CPU side, store data from the CPU side to memory. There should be instructions that would enable to take branch decision, procedure calls, right? Shift the content of the register to the left or right and so on, bit shifting. So typically these are the instructions you need to have in any instruction set architecture. How should I designate my addressing mode? There are several addressing modes you would, like immediate, direct, register, displacement, and so on. And when you would study the MIPS assembly language, you would see that different kind of addressing mode there. So I will not discuss them in detail here. And there are a couple of other issues, that orthogonality, in the sense that the different instructions must be orthogonal in nature. That means that their operations should not overlap too much. Instructions should be independent of each other. Otherwise, there will be redundancy. And obviously, the set of instructions must be complete. There are alignment issues also, like big endian, little endian, also that would be discussed later on. Now, on the top of it, this instruction set architecture governs both hardware implementation in the downward direction and the compiler design in the upward direction. Okay, so any question here?
No, sir.
Okay, let me give you a very simple example. In your lab course, you will study this MIPS and you will write many programs using MIPS assembly language. So I would discuss two instructions here to show the attributes or properties of MIPS. Oh, by the way, this MIPS, when you talk about MIPS assembly language, this MIPS stands for microprocessor without interlocked pipeline stages. This is basically refers to a RISC computer which was built by the MIPS Technologies Limited in 1986. And the word MIPS has also another meaning or another connotation. It's in context to the performance of a machine. It's called million instruction per second. So you might say the MIPS value is this. That means the machine is capable of executing so many million instructions per second. So the word MIPS has two connotations in the context of computer architecture. Sometimes it refers to a processor and the assembly language, and also it refers to million instructions per second. Okay. Now let us now focus on this MIPS assembly language that you would be working on in your lab course also. So here there is a lot of uniformity. The length of every instruction. So we are talking about the number of bits present in each instruction. So the length of every MIPS instruction is 32 bits. So it's uniform. Whether it is an add instruction, branch instruction, or load instruction, everything is accommodated within 32 bits. Memory is considered to be byte addressable. It is organized as bytes. It's byte addressable, but word organized in the sense that when you are transferring something, or when you are talking about this different kind of operations, we are talking about words, and each word comprises 4 bytes. That means again 32 bits. But each byte is addressable. The address bus is 32 bit again. So everything is 32 in MIPS. So therefore, the size of the logical address space, that means that many bytes you can access. You can address. 2 to the power 32 bytes means 2 to the power 30 words, because each word comprises 4 bytes. So many words you can address in using MIPS assembly language. So length of every instruction 32 bits. Length of every word is 32 bit. Width of the address bus also 32 bit. There are 32 on-chip general purpose register. And therefore, in order to designate or identify these registers, you need 5-bit ID, right? because 2 to the power 5 is 32. So you need a 5-bit string to designate one particular register. Clear? And all integer floating point data that is represented as 32-bit in single precision. An opcode in each instruction that comprises 6 bits. So that is the overall MIPS architecture. It's very simple. Everything 32, easy to remember. 32 general purpose register, width of the address bus 32, memory is 32 bit address, length of every instruction 32 bits. Now I give one MIPS instruction here. So it's a collection of assembly language or machine level instruction which are executable by the hardware. One example is this. Add I $T0 S1 5. So can anybody tell me what does it mean?
Add immediate.
Add immediate, right? Add immediate. So what kind of actions are to be taken?
So add S1 with 5 and store it in T0. I don't know which the destination register is.
Destination is T0.
Yeah, so S1 plus 5 and then store it in T0.
You are right, but you should say the content of S1,
Yes, yeah.
Okay. You should say the content of S1.
S1. Yes,
content of S1 is added to 5 and then the result is stored in T0. Remember that the size of S1 is 32-bit, size of T0 is also 32-bit, right? And this is 5. Okay, and this is added. So everything, I know I already just told you that the length of the instruction is 32 bits, right? So there are 4 items here. One is add I, one is $T0, another is $S1 and 5, right? So there are 4 pieces of information here, right? So these 4 pieces of information must be encoded in an instruction whose length is 32. Clear? And that's how you encode it. Okay, so the opcode is 6-bit. For add immediate, the opcode is this. For T0, these are the codes. Okay, and this is 5. Now, one interesting thing is here, the content of these registers, these registers are 32-bit long, right? But you have to add this value to this 32-bit content here, right? No, and the entire instruction is 32-bit long. 6 bits are gone for opcode. These 5 bits are gone to designate this register. 5 bits are gone to identify this register. So you are left with how many bits here? 5 plus 16. 5. So 16 bits are here. So now you have a problem, So this 5 is saved here, right? Using 2's complement in 16-bit, right? But the content of S1 is 32-bit. So you have to add a 16-bit string to a 32-bit content. So that means in hardware, you need to do something else. Do you appreciate this problem? Content of S1 is 32-bit, but 5 is encoded here as a 16-bit 2's complement number.
So what is the problem? The fact that we only have 16 bits access, or that the number of bits in the two things are different? Like one is 32 and one is 16. Because you can always put the 16-bit value into a 32-bit register and add them.
Well, see, the thing is, you have a budget of 32 bits for the instruction, right?
Yes, sir.
So now 16 bits are gone here to designate the opcode and 2 registers, fine? So you are left with only 16 bits. So whatever immediate value you have here, that must be representable. This may be positive or negative. And whatever value you have here must be representable within these 16 bits, because you have only a budget of 16 bits left.
Yes, sir.
Good. But now just look into the job of the addition, the adder. The content of S1 is 32-bit. So one input is 32-bit, the other input is 16 bits.
So we load that 16 bits into a 32-bit register and just put zeros in the upper 16 bits.
That's why. That means you need to do sign extension, right?
Yes, sir.
If it is a negative number, then you have to fill it.
You put one.
Then what sort of filling up you need to do?
Put ones.
Yeah, put ones, right. Otherwise, you have to put zero. So that thing I want to point it out. So that means in the hardware, you need a mechanism for executing this, that you need to sign extend it. If it you need to check whether this bit is zero. If it is zero, then fill the remaining 32. In order to fill a 32-bit string, they put all zeros here, or if it is one, you put all one here, right? So that must be undertaken. That job must be undertaken by the inbuilt hardware. That's what I'm trying to say. I would like to say. Right? Okay, so here the content of add 5 to the content of S1 and save the result in S0. Okay, so this is one example. Here is a complicated example. What is it? Load word.
Load word from memory to a register.
From which location of the memory?
T2, like the value in T2 minus 40. Or
value in T2 means T2 is a 32-bit register.
So that will have some 32-bit value and we subtract 40 from it. That will give us some other value. That will be the index of the RAM or memory we want to access.
Yeah, so that will be the address of my memory location, right?
Yes, sir.
From where I need to fetch the data. Okay, so here one thing now for this I also need a 32-bit instruction to encode this. All right, because every instruction is 32-bit long. Let us see that how you can allocate different bits to designate this instruction. Okay, load word. I know that the opcode should need 6 bits. So 6 bit, there are certain bits, bit pattern here to designate load word. All right. So there are 2 registers here. One is called the source register. This is the source register. This is the destination register. This T2, the identity of T2 is designated here using 5 bits because there are altogether 32 registers. So in order to designate one register, I need 5 bits. So the bits starting from the 21 to 25. So there are specific bits in the instruction, and the hardware actually interprets accordingly. Which one is the source, which one is the destination, and so on. And the destination register is encoded here in MIPS from 16 to 20, these 5 bits. All right. So this source register and destination register and the load operation has been, they have been encoded. Now you are left with this offset value, minus 40. As you can see that you are again left with 16 bits only here in the instruction. So this 40, using these 16 bits, you need to encode this part. So that means this offset value, it could be plus or minus, positive or negative, and that must be representable in 16-bit 2's complement. So there are certain limitations. There are some bounds on this value. You cannot have an arbitrary value here. That must be representable within 2's complement 16-bit 2's complement number. Clear? Now you please tell me that now recall this von Neumann architecture. Now you please tell me that what kind of actions are being taken here. Okay, so this is 40 and 40 is designated here. All right. So it's a 16-bit 2's complement number representing this immediate or the offset value. Well, I should not say the immediate value. I should say it is an offset value. So you have this register, processor, PC, the program counter, and memory, right? So what are the actions that are to be taken? So first of all, just tell me from the first step. Assume that the load instruction has not yet been fetched from memory.
So the program counter will have the address at which the load instruction is stored.
Good.
And it will fetch the instruction and then it will decode it. And if and then there'll be the data fetch cycle. So that's when the what do you call it? Address stored in T2 minus 40 will be loaded into the program counter and the memory will be fetched. And then the instruction execution cycle will be performed where it will be stored when the data stored in that particular address location will be stored in T1. And that's it. I think that's the.
But yes, you said correctly, but there is one thing, one small issue. Remember that program counter always points to the address of an instruction, not data.
Okay.
Okay,
But,
so in the when you want to fetch data from memory, that should not be loaded into that address, after you compute this 40 minus 40, T2 minus 40, that is the address of the memory location from which the data has to be fetched, right?
yes, sir.
That address you should not load into program counter. That should be loaded in a separate data address register. Because program counter is reserved only for storing the address of instructions, not of data.
Okay.
So remember this definition. Remember this subtle point. That's why I ask you to explain the sequences. One thing you can see that how many bits are being what are the number of bits getting having transactions across this interface. So this is the interface where the bits are going from left side to right side and again being transported back to from right side to the left side, right? And since memory is inherently slow, so the number of bits which is being transferred to and from across this boundary, across this interface, that will determine the overall speed. Agreed? Okay. So here, first of all, you said that the address of this instruction has to be loaded here into the PC. That address has to be passed here. How many bits you pass to memory for the address? For MIPS?
5.
32 bits. Isn't it, sir? Each address comprises 32 bit. So 32 bit address has to be passed from left to right. And then this instruction has to be fetched from memory. What is the length of this instruction? Again 32 bits. So now 32 bits will pass from right to left. So the instruction has been brought in the processor. Okay. Now you compute this address of memory, address of data. And again, this 32-bit data address has to be passed here from processor to memory. The data has to be retrieved and that data has to be passed again to the processor side, again 32-bit. So how many bytes are getting transacted? So many bytes are being transacted, from left side to right side and right side to left side. See, that slows down operation, So when you say load what T1 minus 40 S2, things are not so easy, There are many intermediate actions or micro actions taken by the machine, one after another. And everything is under machine control. And that is the job of the hardware or the CPU, the underlying hardware, to take care of, to synchronize all these actions one after another. Here, I want to mention one thing, that MIPS, this MIPS assembly language or the MIPS machine is based on what is called the load store architecture. So here, all instructions are broadly classified into two types. One is called memory access. That means where you access data from memory, or both way, like loading from external memory or storing into external memory. So you access memory and load the data from memory to a register here. And similarly for store operation, you store the content of some register back to memory, back to some memory location. So those are load store. And ALU operation, when you talk about ALU operation like addition, subtraction, or logical operation, so they involve only internal registers, only registers here. for ALU operation, you don't have to access memory. You got the point? So that's why it is called load store architecture, meaning that all memory actions, memory access for data, that is separated. Okay, do you get the point? I mean, I cannot write in MIPS assembly language an instruction like this that add like ABC. That you access the content of memory location B, you access the content of memory location C, and then you add those two content and save the value in A. I mean, addition and memory access cannot be done simultaneously in MIPS architecture. So that's why you need to execute load instruction first in order to access the required data from memory to the processor side, and then execute the ALU operation separately. When you do ALU operation, it involves only internal registers like this, as in the previous case. See, when you do this, this is an arithmetic operation, ALU operation. It involves only registers. There is no memory access here. Clear? Memory access should be done separately using load operation and store operation. That's why it is called a load store architecture. However, the Intel processor chips, they are not load store. They support complicated instructions. You can perform arithmetic operation and memory access same time at the same time in the same instruction. Those operations are those instructions may be there, but in MIPS architecture they are clearly separated to make the hardware very simple. So as you said, this meaning of this load instruction is the following. You look at the content of this register, RS here, the source register, and then you pick up this 16-bit 2's complement field, consider this as this offset, and you do sign extension to make it 32 bits, add the value, add the offset value to the content of this register to form the data, to form the address of the memory location, and then access the memory by passing this address and retrieve the content of that memory location and store the value in the destination register. So symbolically, it can be written in a short way, in a short form like this. All right. Okay. Now let us move into a little bit quantitative issues, and this is concerned with what is called the CPU performance equation. So today we have a few more minutes, and so we can discuss this. Amdahl's law maybe in the next class. Okay, let me skip this thing, Okay, so let me define one thing. Now, first of all, please tell me that as a programmer or computer user, what would you want? You have written a program in high-level language, and you have submitted your job to a processor, and you expect that the processor would execute it and finish the job and will deliver the output. So, what do you want? From a user's perspective, what is your expectation?
Fast execution.
Right, very good. Fast execution. Right? That means you want to have a very fast CPU time. This is because such a component is known as, this is called a response time. So as a user, you submit a job to a processor. You submit a program P or a job, and then after some time the job is completed. Now, in a multiprocessor system or in a computer floor, this may depend on the overall system load. How many users are being simultaneously present there, and so on. So this is called the response time. This response time also includes the time needed for doing your input-output. It also includes the time required by the operating system by compiling your program and so on. Okay, and other system software that is necessary to manage your programs. And it also includes what is called the CPU time. Right? So response time includes CPU time plus some additional overhead due to OS and compilation and so on. Now CPU time means it is the time which is needed for executing the machine code of P on the on the processor itself, including the memory access time, but excluding compile and operating system time. So it is the time exclusively required by the machine for executing your program. Of course, it includes memory access time because memory you have to access anyway during the course of execution. So we are concerned now. We will try to find out. Can you write down a formula or an equation that would express CPU time in terms of some fundamental things? Response time is CPU time plus some additional time for needed by operating system, input, output, and so on. In CPU time, we do not include that. All right. So performance, we say that performance is proportional to the inverse of CPU time. So that means if the CPU time is less, it means that you finish your program quickly, and we want that. And as an user, you want to have your performance higher. It means that you need your CPU time to become very small as possible. So let me ask you this question. You have some understanding of this computer architecture now, this von Neumann case, and you know that how the machine language program is executed one after another. And you have several steps in the execution cycle and so on. So imagine that you have a program P, and that you have already translated into assembly language or machine language. And the job is submitted to the machine M, and I want to see what are the factors that would determine my CPU time. So what are the factors on which my CPU time would depend? Given this scenario that I have an assembly language program P or a machine level language program P equivalently when submitted to a machine M. So have some thought on it and try to give us some pointers.
The type of the instruction, like ALU instructions, probably take less time than load instructions, which access memory.
Yeah, that is one issue, but we'll discuss later on this, because if the time of instruction vary, then there may be difficulty in synchronizing the pipeline, right? Because you have to keep track of, because then it will be variable time instruction. If the execution time differs, then it will be an additional overhead for the controller to manage that. So for simplicity, let us assume that all instructions are of, more or less same. Number of instructions is one thing, right? Instruction count. So P consists of a number of machine level instructions. IC is the instruction count. Obviously, it will depend on the number of instructions, right? In the machine language. Right?
Yes, sir.
And each instruction requires some machine cycles. Right? Remember that is instruction fetch, decode, execute, memory access, write back, and so on. Recall the load instruction. What are the actions are needed for executing the load instruction? There are so many steps, right? So each machine instruction requires several clock cycles to complete. And these clock cycles, as you said earlier just now, that these clock cycles may vary, Of course, it may vary. So let us consider an average of that. So average number of clock cycles per instruction. So you have instruction count, average number of clock cycles per instruction. What else? I want to compute the CPU time.
The time required, like the time for one clock cycle in seconds.
Yes, and that is called clock cycle time, CCT. Each clock cycle has certain time period, and this is called clock cycle time, CCT. So you have this fundamental equation, and throughout this course this course will revolve around this equation only. It's a very simple equation. CPU time is equal to instruction count into number of clock cycles, average number of clock cycles per instruction times clock cycle time. Right? So you have the full picture in front of you now. So everybody wants to minimize the CPU time. So if you can minimize these components, one or all of them, then your CPU time machine would be faster. Your performance would become better. So if you can write a program such that after compilation and after doing assembly language translation, the number of instructions becomes fewer, then it might have an impact on the CPU time, right? If the CPI value, the average number of clock cycles per instruction, becomes smaller, then the CPU time would be improved. Similarly, if the clock cycle time, if it is reduced, then the CPU time would increase. So the question is, okay, of course I can reduce instruction count by writing good algorithms, by designing good algorithms or writing good programs. How would I reduce the value of CPI or the value of clock cycle time?
Sir, is the average of the CPI, is it calculated averaged over a single program, or is the average of all possible instructions and the number of clock cycles they take and we average over that?
Yes, you can consider average over many benchmark. In general, so there are certain benchmark programs, right? And looking into those benchmark programs, you can figure out what is the average value. So in general, the CPI refers to not a particular program, but in general, average number of clock cycles per instructions. But for a given program, you can also think of some CPI. That there are some examples which we will work out later. You will see that given a program, you can, with respect to some particular program, you can also have certain value of CPI depending on how the instructions have been distributed in the code, right?
So this equation is meant to give us an estimate of CPU time. It's not meant to be accurate.
It's an estimate. Estimate is fine, because exact estimation is not possible. Exact computation is not that possible. I mean, it can possible in real time. If you run your program and you can observe the CPU time. That's the real time computation. But this is you are computing in advance. This is an expected CPU time, or an estimate of CPU time, you might say, right? Because in actual practice, depending on the nature of instructions, the number of memory accesses may differ. The memory may slow down, depending on other, there may be cache misses and so on. So there are many issues. So exact computation is not possible unless you are in real time. So this is a kind of give an approximate idea, the estimation of CPU time that depends on 3 parameters, right? The instruction count at the machine level, the average number of clock cycles per instruction, and CCT. And throughout the entire course, when you study this memory hierarchy like cache and so on, we would see that what is the purpose of cache? The purpose of using memory hierarchy or cache or pipelining is to reduce the effective value of the CPI, or the average number of clock cycles per instruction. That we want to reduce by adopting several mechanisms like like memory hierarchy using cache and so on, or by adopting pipelining strategy and so on. All right. And there is another hardware issue which is referred to CCT, clock cycle time. This is known as the famous CPU performance equation. Remember this, very simple to equation and easy to remember. IC times CPI times CCT. So here is an example. Maybe we'll look into this. So there is a problem statement to look into this, that you have a program P and it has 1000 machine level instructions, and it is being executed on a machine M running at 1 gigahertz clock speed. And as you see here, this program P comprises some ALU operation, some load operation, some store operation, some branch operation. And there are 40% ALU operation like addition, subtraction, logical operations, and so on. There are 20% load operation, that means load some data from memory. Similarly, there are 10% store operation, store some register content back to memory, and there are 30% branch operation, like branch on positive, branch on zero, and so on, if then else sort of thing, right? And let us assume that number of clock cycles here is 1, because this is ALU operation, that means it is CPU bound. So number of clock cycles is required small. This is load operation, that means it is memory bound, and therefore it is little slower and it needs more operation. We have just seen that load operation is quite complicated. There are so many transactions you have to perform, right? So assume that the number of clock cycles is 2 here. Similarly, store is also memory bound. So 2. Branch operation, let us assume that it is 2. So you have this frequency. These are the percentage of different kinds of operation, and these are the clock cycles needed. So estimate compute the CPI value and the CPU time. So how do I compute the CPI value? Very simple. 1 clock cycle needed for 40%. So 1 times 0.04. 2 clock cycles needed for 20%. So 2 times 0.02 and so on. So sum them up. So CPI is 1.60. So average number of clock cycles per instruction. So that means you need more than 1 clock cycle per instruction on the average, because some instructions takes longer time to compute, isn't so? So this is the average value of the CPI time, CPI, with respect to this particular program. And then given this, since we have the number of instructions is 1000, you have the frequency. What is the relation between the frequency and the clock cycle time? Frequency is 1 gigahertz. So what would be the clock cycle time?
One nanosecond.
Yes, 1 over 1 gigahertz, right? Inverse of, reciprocal of the clock speed, right? So you have the number of instructions, you have the CPI value, you have the clock cycle time, then you can estimate the CPU time also. Okay, so CPI value we have just computed is 1.60. Number of instructions in the program is 1000. Clock cycle time is 1 gigahertz. So CPU time is, we know that IC times CPI times CCT. IC is 1000. CPI, average number of clock cycle per instructions for this particular program, is 1.60 times 1 by 1 gigahertz. That means 10 to the power 9. Right? So this is, so the CPU time is this 1600 nanosecond. So given the attributes, certain parameters of the program you are going to execute. If these parameters are known, you can estimate the CPU time using this very simple expression, very simple formula, right? (1600 nanosecond). In real life, in real practice, maybe it may be a little bit more because of memory access. Here we are assuming that Whenever you want to access memory, you get the data immediately. But in real life, there may be cache miss, there may be main memory miss, and so on. You may have to access into the lower levels of memory and so on. And therefore, the actual CPU time might increase, but this gives you an overall estimation. Got it? Any question, doubt here at this moment, at this stage? So we have worked out one fundamental equation related to our computer organization that gives you an expression for CPU time in terms of instruction count, number of clock cycles per instruction, and clock cycle time. So incidentally, our next class has been cancelled because of we have an institute holiday, right, on Thursday. So we'll be meeting again on next Monday. And I think I would be finished. I would be able to complete this portion, this part, the introduction and CPU performance equation and Amdahl's law in the next class. And then Professor RSC will take over. Any question, any doubt here? Need some clarification regarding any issue?